Here's an explanation for the answer to final exam question number 46 in Electronics Demystified 2nd edition. If you have the printed book, you'll find it on page 426 and 427. We're trying to make a radio frequency oscillator circuit, and we want to know what kind of circuit arrangement out of the following 5 listed would make the best oscillator arrangement. Well, what we do with a radio frequency oscillator in effect is we have an amplifier with a tuned circuit which defines the frequency, and then we have positive feedback so that this signal gets amplified. The tuned circuit makes sure that only a certain frequency gets fed back. This process goes around and around and around in a vicious circle, creating a radio frequency signal. That is what we want to do in order to make an oscillator work. And in order to do that, this amplifier has to be sufficiently effective to ensure that that signal, that feedback signal, can sustain itself. If the amplifier doesn't work well enough, if it doesn't provide enough gain, then this feedback will die off and we won't be able to sustain the oscillation. Or the oscillation might be sustained until we put a load on the oscillator and then it will stop. And we don't want that. We want our oscillators to keep working. We don't want them to fail. So, let's take a look at a circuit that can do that. This is called a Armstrong oscillator circuit. It's a radio frequency circuit that has an NPN bipolar transistor. The feedback takes place from the collector around through here, through this transformer, through this tuned circuit, and back to the base, like that. The transformer inverts the phase. Notice that this transformer reverses the phase of the feedback. And the reason that it does that is because the feedback signal in a circuit like this, from the collector back to the base, is out of phase. The collector signal is out of phase with the signal at the base, so that if we feed it back directly, we will get negative feedback. So to get positive feedback, we need to reverse the phase. That's the basic Armstrong circuit. And this is an effective amplifier, and the reason that it is so effective is that it is a common emitter circuit. Notice that this resistor and capacitor ensure that the emitter is at ground. The capacitor in particular ensures that the emitter is at radio frequency ground. So it's a grounded emitter circuit or common emitter circuit. And that is choice D. Of the other choices, now if this were a field effect transistor here, then we would be talking about a common source circuit, but that's not any of our choices. Common gate circuit with a field effect transistor, choice A, that will provide a stable amplifier but not enough gain. Class C, choice B, Class C, absolutely not. We don't want a weak signal amplifier like this to operate in Class C. We won't get anything at all in oscillation if we try that. Common base, well, that's the equivalent of a common gate circuit. That won't work very well. Class B, again, that's sort of the same situation as Class C. That won't work very well as an oscillator. The best answer to this question of the choices that we have here is choice D, the common emitter arrangement.